The majority of wave optics can be explained by Thomas Planck, who showed that there is a wave-like quality of light, especially in the realm of interference. Although Planck did not account for the photoelectric effect, which is when light hits a metal surface, some of the electrons are ejected from the metal, displaying a particle-like quality of light. These combined demonstrate the wave-particle duality of light.
And Einstein came around. And what it showed is that the wave model doesn't work. Only the particle model works. And so now we've got a duality, this view of light as both a wave and a particle. And so what's the answer? Well, both are right. And so how do we know which model to use? Again, it's a sense of scale. And so if we're looking at objects that are comparable to the wavelength of the light, then we use the wave model. But if we're looking at experiments where the energy is comparable to the energy of a photon, it's going to be a really small amount of energy, then we have to treat them as a particle. And so did you learn to select a model?
So, while light can be tricky in terms of how it is made, it still has measurable quantities such as the speed of light. In 1849, Fizeau set out to create a method to measure the speed of light. This method that he created did so with incredible precision. It consisted of a light beam through a toothed wheel that was then reflected off of a mirror.
He did it with one of these. I'm going to put away the clicker for a second because I want to engage your brains in this. Now, this is a toothed wheel. It's got a bunch of notches and it's got a bunch of teeth. This was Fizeau's solution to sending discrete pulses of light. He put a beam behind one of these notches. If I point a beam through this notch at a mirror 5 miles away, that beam is bouncing off the mirror and coming back to me through this notch. But something interesting happens. As he spins the wheel faster, he notices that it seems like a door is starting to close on the light beam that's coming back to his eye. Why is that? It's because the pulse of light, it's not coming back through the same notch. It's actually hitting a tooth. And he spins the wheel fast enough and he fully occludes the light. And then, based on the distance between the two stations and the speed of his wheel and the number of notches in the wheel, he calculates the speed of light to within 2% of its actual value. And he does this in 1849.
One other interesting property of light is that of reflection. In this image, we made it so that both the hole in the paper, which light was shined through, and the mark on the paper on the far right were equidistant from the center hole punch. This was done to illustrate that the mark on the mirror, which is where the laser pointer hit the mirror, lined up with the hole punch. The fact that the light ended up being equidistant validates the law of reflection such that theta 1 is equal to theta 2 when reflected.
Have you observed the path of light when it strikes the mirror or wall in daily life? Does it move along straight line path or changes its direction? Definition: when light ray strikes the boundary of two media, such as air and glass, a part of light is turned back into the same medium. This is called reflection of light. A highly polished surface, such as a mirror, reflects most of the light falling on it. Laws of reflection. 1. The angle of incidence is equal to the angle of reflection. And 2. The incident ray, normal to the mirror at the point of incidence, and the reflected ray all lie in the same plane. These laws are applicable to all types of reflecting surfaces, including spherical surfaces.